Thank you for listening. My name is Tobias Kroll. My term project was the derivation of empirical potentials with quantum chemical accuracy through Bayesian optimization, which is of course quite a mouthful. So, dealing with the low-level problem description. Again, this is all domain knowledge, which you may not be able to understand. You can either pause the slide or wait until the high-level description, of course. So, where comp sci and chemistry meet is called computational chemistry. And one of the major things they do is use molecular dynamics simulations, which are essentially just a particle simulation that attempts to mimic the reality of what's actually happening. The problem is that to truly accurately do this, which is where the quantum chemically accurate term came from, to do this is computationally expensive, which of course is a common problem. So instead, classical methods use empirical potentials to govern interactions between the particles. And these empirical potentials, or force field, are of course approximations of what's actually happening, and they include a wide array of parameters, both related to the real world in bond strength and van der Waals forces, things like that, and parameters that govern the actual computation of the simulation. So, there needs to be some means to calculate the approximate model for some set of conditions from the actual realities. That's where my project comes in. So I wish to write a program that can, given a set of structures and an energy differential or pair correlation function, produce an empirical potential that closely models the actual quantum chemical processes. So, with all of that domain knowledge out of the way, on a high level, this is an optimization problem. We are attempting to minimize the difference from our approximated solutions to the actual solutions. So in the case of my project, I am mostly looking at energies of some structure system. So I wish to calculate these energies given my force field approximation and compare them to the quantum chemically calculated energies in that system. And that's how we make an objective function. It's just an error function. So, function optimization is not by any means a new problem, and it far predates machine learning techniques. So why use Bayesian optimization at all? There's three particular points. So the actual function is unknown. So that's part one, and it just means you can't analytically solve it. As computer scientists, we're used to that, which is why we make iterative methods. The function is also rough. Again, not new, but it means we can't use simple local solvers, such as gradient descent or conjugate gradient. And last but not least, this is probably the most important sticking point, is that the function is expensive to evaluate. So every time I want to calculate an energy value from my molecular system, I need to run a step of an MD simulation, which takes around 5 minutes for most systems, which is a problem because we're trying to optimize for 10 to 40 parameters, which means we're in up to 41-dimensional space, which means we need a lot of sampling of the objective function in order to solve it. So we cannot just randomly select points to sample. So we cannot do stochastic gradient descent, and nor can we do the lengthy process of, for example, using hill climbing in concert with gradient descent. So that's all not possible. So, but those 3 points are things that Bayesian optimization doesn't care about or solves well. So it doesn't require knowledge of the function. It takes in a black box function. It's a global solver, which is great, and then it seeks particularly to minimize the amount of objective function evaluations. This is not new. In fact, I think we talked about it in the last 2 lectures, essentially. So instead of sampling randomly, you sample at some optimal point. The optimal point defined by some function of trade-off of exploitation versus exploration, and you do it often enough, and then you converge towards a solution, which is of course optimal learning versus just learning. Some finer points. So that optimal point to sample is determined by maximizing an acquisition function, which again is some trade-off between exploitation and exploration. Here is an example. It's called expected improvement. As you can see, this function requires the mean at x. It requires cumulative distribution function, standard deviation, and probability distribution function. So we need knowledge of some normal distribution at x. Luckily, we have something called Gaussian process regression, which I cannot explain in the 10-minute limit. However, what this does on a high level, it has a kernel, and the kernel determines the likeness of one set of data to the next. So for example, if we're sampling at a location that we haven't sampled before, it compares that likeness to the samples that we do know about. And not only does it make a function and a mean, it also makes a distribution at any given x of uncertainty. Altogether, this is called the surrogate function. And now, somewhat funnily, of course, if you read that first bullet again, we're optimizing some function, an objective function, by optimizing an acquisition function and surrogate function, which sounds circular, but of course, again, if the point is to reduce the time, and particularly the time for our objective function is very, very long, and the time to optimize our acquisition function is very, very short, then of course we're saving time, so it's all great. And even better, because the acquisition function takes such a short time to evaluate, we can use stochastic gradient descent, which means it's embarrassingly parallel, which is very important because in the end, even with Bayesian optimization, some of these things take days to optimize totally. So, here, a picture of the process sourced from a paper by Liu and Boshi. So, in a predecessor, essentially, of what I'm doing, you take the initial data set, right? So you have some points at which you already know the answers to your characteristics, and then you plug it in to your Gaussian process regression, which will let you solve and optimize the acquisition function. Then you take the argmax of that acquisition function, right, the point you want to evaluate, you plug it into your MD simulation, and then you add it to your data set, and then you start again. So just like any normal iterative method of solving a function, and then at the end, you converge, and at some point, you choose the minimum you have. So that is what I did. And this is what it looks like here on a simple function. So this is just a sine function, right? Use x and y. Green's the prediction, and you have the slightly transparent red areas. Those are 95% confidence intervals from our surrogate function. And then you have the red line, which is the real objective function, and you have the two observations. And on the bottom, you have the expected improvement function. So we would expect to sample at the very left of our allowable space. As you can see, obviously, our prediction does not currently come close to matching the objective function because we only have 2 data points. So it's impossible to properly analyze the function at this point. But just 9 points later, and note, by the way, that we did sample on the very left, as you can see there, 9 samplings later, not only have we found the optimal solution, we have in fact approximated the entire function with almost no error, which of course is great, because that's what we want. And of course, a sine wave is relatively simple and almost entirely matches the kernel picked for this particular Gaussian process regressor. But the picture is not that different from actual solutions. They're just in very high dimensional space, so they're hard to show. But in general, this was successful. So one more time, I'm running through very quickly. Computational chemists use MD simulations, and those of course take parameters. How do we find the parameters? I chose Bayesian optimization, again for all those reasons I gave, and I think I was relatively successful. So thank you for listening.